So the next step is the inference. So, well, okay, we know how to find B0, B1, Bk by just minimizing the SSE, right? And it turns out that, well, B is equal to X transpose X inverse times X transpose times Y. That's good. That's how we find B. But remember, so once you just give any values of X and Y, you can find a value for B. So the main thing is to just check whether these B values can be used to make predictions for the future values of Y or not. Okay, can we use them or not? So what we will do is we will just make inference. That is, we will make hypothesis tests and confidence intervals. Remember, the results was given in the table below, so we just see them. But now we will give the technical details of them. So, well, B0, B1, Bk, well, they are unbiased estimators for beta 0, beta 1, and beta k. So you can say, sorry, you can just say, let me just erase this like this. Expected value of, let's say, Bi, that's equal to the beta I, right? So this is an unbiased estimator. Each Bi or each Bj, let's say, because I guess we are just using I for observations. So Bj is equal to beta j, the expected value of Bj. This means that, well, this is an unbiased estimator for the parameter beta. Then the following, this one, Bj minus beta j plus S of Bj. Remember, we have exactly the same thing in the simple linear range, right? So this thing, which is equal to, so instead of S of Bj, remember we say that so this is the X transpose X inverse matrix, okay? So we say that the diagonals of these matrices, okay, this, and this, they just show, if you are multiplied it by sigma squared, they just give the variance of the variance of Bj, right? So what I have here, S times square root of Cjj. So let's say this is Cjj. Right? If you just take the square root of this, so it was something like this, Cjj times sigma square. It just gives you the sigma square of Bj. So if you just take the square root of this is equal to sigma times square root of Cjj. And instead of sigma, I'm just using its estimator S, right? So this is what? This has a T distribution, okay? That's a great news. With n minus in square, in parentheses, k plus 1 degrees of freedom, or n minus k minus 1 degrees of freedom, okay? Well, we can just use this to construct the confidence interval or to just make the hypothesis test. How? So if you just want to test beta j is equal to 0 or not, then you can just see this. The observed is equal to Bj, which is calculated, okay, from the equations divided by S times square root of Cjj, again calculated from the equations. If you just put them, you see the T observed, and just you can compare it with the critical value of T to see whether you can reject the hypothesis. Or you can just construct confidence intervals how beta j is an element of what? Bj plus minus T alpha over 2 times S divided by square root of Cjj, right? Okay, great. So in fact, this is just telling what I have told a little ago. Okay. And in the following, we will talk about the ANOVA. Okay, we will talk about the ANOVA in multiple linear regression. Right? So as we said in the introduction part, the partitioning is the same. Okay, so yi minus y hat. This is the total deviation. This is the deviation around the predicted mean. Okay, so this is my predicted mean by using the linear regression. This is the deviation around the predicted mean, and this says this is my prediction, and this is the overall mean, and this is the deviation around this is the deviation of my regression line around the mean, right? So the total variation is equal to the variation of the line around the mean plus the variation around the line, okay? So as I said, we just covered this in our example. Well, you have the first thing is, well, you have the degrees of freedom, k here, n minus k minus 1 here, and this is n minus 1. If you just sum them up, it just gives this one. And SSR plus SSE, it's also equal to SSD. The next step is you just divide SSR by k and SSE by n minus k minus 1 to find the MSR and MSC. And this is the F ratio, this is the F observed, okay? And last you have the P value, the significance, right? And you are just testing whether all of the betas are equal to 0 except a beta 0, right? Except beta 0. And we just use this test statistic, and this is my decision rule, remember? So K degrees of freedom, this is the first source of ingredient for the F random variable. And this is the second source, n minus k minus 1, which is here, right? So this is the F value, which leaves an area of alpha to the right. If it is greater than that, then you just reject the hypothesis. So it's something like this. This is my F random variable. So this is F alpha, right? This is alpha. And this is F of alpha with k and n minus k minus 1 degrees of freedom. Okay, so okay. And if your F value, if your F observed is greater than this, if it is somewhere here, then you reject the hypothesis. Okay, so if H0 is rejected, we decided at least one of the coefficients is not 0, right? If just one of them, I don't know which one, but I know that, well, at least one of them is not 0. So if H0 is not rejected, well, we conclude that the data do not support the existence of a linear relationship between y and any of the variables x. Okay, so if it is not rejected, this is what we have. If it is not rejected, if you cannot reject the hypothesis, what is the hypothesis? It says you have all of the betas except beta 0 equal to 0. Then, okay, the data says that, well, you don't have any linear relationship between y and any of the x values, okay? So as we did in simple linear regression, we can just make hypothesis tests about beta i's. We can just construct confidence intervals on beta i's. Then we can just find confidence intervals for the mean response, okay, expect the value of y. And we can just find prediction intervals for, again, for single responses for a given set of xi values, okay? So for a given set of xi values, I can find the mean response and I can find a confidence interval for the mean response and a prediction interval for a single response, okay? Well, most of the time you won't need to make it through your hands, okay? Because we will have the computer output, and most of the time we will try to comment on the outputs of the computer, okay? Most of the time, either Excel or R, but most of the time we will just deal with the computer outputs. You have to know them, okay? You're responsible for them, but as I said, most of the time we will use the computer outputs.